All right. Hello, everybody. I wanted to do just a couple more induction practice problems, um, because it's kind of tricky and just takes a little bit of practice. The number one thing to keep in mind, really, with a lot of different proofs is what you're starting with, you know what your destination is. And so keeping faith and kind of always looking at what your destination and crafting your expression to look more and more like the destination. So I'm looking at example number two on page 50. I'll do just a couple of the first couple examples. I don't want this video to get too long, and sometimes it takes a while. Okay, so here is 2a. We've got 1 squared plus 2 squared plus 3 squared all the way up to n squared, and apparently this equals 1/3 times n plus 1 times n plus 1/2. So first step is let n equal 1. What does that look like? The left side is just 1 squared. The right side is 1/3 times 1 times 2 times 1.5. And that actually cancels all out right there because 2 times 1.5 is 3 times 1/3 is equal to 1. So we have 1 is equal to 1, and we're happy. Then the second step is going to be assume, I'm just going to write it in sigma notation because it's a little shorter. Assume k equals 1 to n of k squared equals 1/3 n times n plus 1 times n plus 1/2. And then we look at the inductive step here. So we look at, I like to write the word consider, k equals 1 to n plus 1 of k squared. That's going to equal k equals 1 to n of k squared plus one more term, n plus 1 squared. Then right here's the crucial thing. We're always going to use our inductive step. We're always going to use that step. So let's do it right there. So now what we have is the formula 1/3 times n plus 1 times n plus 1/2 plus an extra n plus 1 squared, because that's the new term. That's the next domino in the line. It's also sometimes nice to write out what your goal is. Pink is a good color for the goal. Remember that the goal is this same induction hypothesis plus 1 for our n value. So we want to get somehow n plus 1, n plus 2, n plus 1.5. That's our goal. And so what I notice is that our expression that we're working with has an n plus 1 in 2 spots. You could, of course, multiply everything out, but that would get pretty hairy. So I'm just going to look for commonalities. There's usually something that's in common. So I'm going to factor out an n plus 1 from both of those terms. The left term has remaining a 1/3, an n, and an n plus 1/2. The right term has remaining an n plus 1. Okay, I don't see anything fancy, so we're just going to multiply out this inner expression. So we have n plus 1, and now we'll go 1/3 n squared plus 1/6n plus another n plus 1. Okay, that's a little weird, but we'll try to work with it. Okay, so then what we have is n plus 1 times 1/3 n squared plus 7/6 n plus 1. And so what I'm trying to do when I look at this is I can see I've already achieved n plus 1. Okay, so somehow the rest of that I need to get an n plus 2, an n plus 1.5, 0.5 and a 1/3 out of it. So I think I'm going to pull the 1/3 out here and then see what's remaining. So let's do this. Let's create a little space up top for me to write on. I think we could get there in about 2 or 3 more steps. So, all right, I'm going to copy all that junk back up top here. Whoop. We're going to pull 1/3 in front of the n plus 1. So when you factor something out, it feels like you're dividing the terms. So that becomes just a regular n squared. Now, if I take 7/6 and divide it by 1/3, I get 7 over 2n. And if I take 1 and divide it by 1/3, then I get 3. Just think about distributing that 1/3 back in. And you should see how I got that. Now, the last thing, we know what that should factor as. This part here should factor as these two pieces right here. Yeah, and if we rewrite this in terms of its decimal form, you can even see a little bit clearer why. This is 1/3 times n plus 1. This right here is the same as 3.5. And so I'm thinking of two numbers that multiply to make 3 and add to make 3.5. Turns out n plus 2, n plus 1.5 do the trick. Proof by induction. Okay, so that's the end of the proof right there. So that was question 2a. I think just to keep the video short, I'll do the question 2b in another video. Like, comment, whatever you need. Let me know how I can help you.